Hi friends, welcome to my channel. Consider an ideal PMOS capacitor of area 100 micrometers into 100 micrometers operated at T equal to 300 K. Phi m brackets law work function for the metal equal to 5.2 electron volts. X naught means oxide thickness that equal to 3 nanometers and Nd equal to 10 power 17 per centimeter cube. Question is calculate the flat band voltage VFB and the threshold voltage VTP assuming EOX equal to 3.43 into 10 power minus 13 farad per centimeter, VT of thermal voltage equal to 0.026 volts, Ni equal to 10 power 10 per centimeter cube, SI equal to, that means electron affinity of silicon equal to 4.05 electron volts, and ESI equal to 10 power minus 12 farad per centimeters. Farad per centimeters. Please remember, flat band voltage VFB is the gate voltage at which the semiconductor's Fermi level aligns with the intrinsic Fermi level at the surface, resulting in zero band bending. Formula for an ideal MOS capacitor, the flat band voltage is given by VFB equal to 5 ms minus 5 ms separate to minus separate to QOX by COX, where 5 ms means work function difference between the metal gate and the semiconductor in volts. QOX means effective oxide charge per unit area in C per centimeter square. COX means oxide capacitance per unit area in farad per centimeter square. Factors affecting are work function difference, oxide charges, non-idealities. Okay, non-idealities. So given data, Q 5m equal to 5.2 electron volts, 5m equal to 5.2 volts. Oxide thickness equal to X naught equal to 3 nanometers. Nd, it should be Na equal to 10 power 17 cent per centimeter cube, that equal to Na. Epsilon Ox equal to 3.43 into 10 power minus 13 farad per centimeter. Vt equal to 0.026 volts. Ni equal to 10 power 10 per centimeter cube. Si equal to 4.05 electron volts. Epsilon Si equal to 10 power minus 12 farad per centimeter. Eg equal to 1.1 electron volts. Now calculate oxide capacitance per unit area. COX equal to epsilon Ox by XOX, that equal to 3.43 into 10 power minus 13 whole by 3 into 10 power minus 7, that gives you COX equal to 1.143 into 10 power minus 6 farad per centimeter square. Remember, that is the first we have calculated oxide capacitance per unit area. Now from the diagram, first P type material untadi, then EV vastadi, EF vastadi, then EI vastadi, then EC అని వస్తుంది, ఈసీకి ఈఏకి ఈసీ బై 2 అని వస్తుంది. ఈ vacuum, the distance between EF to E vacuum is Q phi s. The distance between EC to E vacuum is Q xi s. Q xi s. Then P naught is approximately equal to Na equal to Ni into E power Ei minus Ef by Kt. Ei minus Ef equal to Kt natural log Na by Ni. Ei minus Ef equal to 0.026 electron volts into natural log 10 cube by 10 power 10. So Ei minus Ef equal to minus 0.419 electron volts. Now the equation Q phi s equal to Q phi s ante E vacuum to E Fermi level, that equal to Q xi s x2 means that is Q xi s nada, that is E vacuum to EC plus EZ by 2 plus Ei minus Ef plus Ei minus Ef. Remember once again, Q phi s equal to Q xi s2 plus Ez by 2 plus Ei minus Ef. Substitute చేస్తే Q phi s equal 4.05 electron volts plus 1.1 by 2 electron volts minus 0.419 electron volts. Q phi s equal to 4.181 electron volts, that equal to phi s equal to 4.181 volts. Now flat band voltage VFB equal to 5 ms equal to 5m minus 5s, 5m minus 5s, that equal to 5.2 minus 4.181, 5.2 minus 4.181, that equal to 1.019 volts. Phi f equal to Fermi potential phi f equal to Vt natural log Nd by Ni, that equal 0.026 natural log 10 power 17 by 10 power 10, that equal to 0.419 volts. Then threshold voltage V threshold equal to V flat band plus root over 4q Na epsilon SI phi f by COX. Here the numerator part is root over 4 Q NA epsilon SI phi f. Denominator part is COX. Separate వస్తుంది VFBకి ఇది plus 2 phi f. Substituting the value you will get 1.8692 volts. In the circuit shown in the figure below, M1 serves as an electronic switch. If Vin is very small, determine the W by L such that the circuit attenuates the signal by 5%. Assume Vg equal to 1.8 volts and RL equal to 100 ohms. Mu n COX equal to 200 microamperes per volt square and VTN equal to 0.4 volts. ఇక్కడ N channel MOSFET కి arrow is towards the drain ఉంటుంది కదా. Input is given to Vin and Vg is the gate voltage. The transistor is defined as M1 and for that source ki Vout తీసుకున్నాం. source ki Vout ki series with RL, then Vout is taken output of the RL. So if Vn is very small, VDS is very small, hence MOSFET is in linear region, it acts as resistor. IDS is approximately equal to mu n COX W by L VGS minus VT into VDS. Then VDS by IDS equal to R equal to 1 whole by mu n COX W by L VGS minus VT. Given VGS equal to VG minus Vout, that approximately equal to VG equal to 1.8 volts. So ఒక R రాస్తాం, Vout తీస్తాం, దానికి ప్యారల్గా RL వేస్తాం. ఓకేనా? సో ఆర్కి ఆర్ఎల్కి మధ్యలో Vout తీసుకుంటాం. Vin is the input. Then Vout equal to 0.95 Vin. Vout by Vin equal to 0.95. Now Vout equal to Vin into RL by R plus RL. Vout by Vn equal to 100 by R plus 100. That equal to 0.95. R equal to 5.263 ohms. W by L equal to 1 by mu n COX VGS minus VT into R. W by L equal to 1 by 210 power minus 6 into 1.8 minus 0.4 into 5.263. W by L equal to 678.6. The question is, find the voltage V0 in the circuit shown in the figure using source transformation. Also find the power developed by the 250 volt voltage source. An element in parallel with ideal voltage source is redundant. An element in series with ideal current source is redundant. So 5 ohms ఈ యొక్క 100 ohms ఈ 5 ohms అయితే రిమూవ్ చేస్తాం. సో 250 volts ఇన్ సిరీస్ విత్ 25 ohms 8 amperes 2 ohms అనేది రిమూవ్ చేస్తాం. డైరెక్ట్ 100 ohms దగ్గర పొటెన్షియల్ తీసుకుంటాం. ఓకేనా? దాన్ని ఈక్వలెంట్ సర్క్యూట్ డ్రా చేస్తాం. నెక్స్ట్ 250 volts 25 ohmsని ఎలా రాసుకుంటామంటే 10 amperes కరెంట్ సోర్స్ తీసుకొని 25 ohmsలో షంట్లో వేసుకుంటాం. 8 amperes కరెంట్ సోర్స్ తీసుకొని 100 ohms తీసుకొని దానికి ప్లస్ ఆర్ మైనస్ U0 క్యాలిక్యులేట్ చేసి దానికి 15 + 5 20 ohms తీసుకుంటాం. నెక్స్ట్ దాని ఈక్వలెంట్ 2 amperes కరెంట్ సోర్స్ వస్తుంది. ఇన్ ప్యారల్ విత్ 11.11 ohms అని వస్తుంది. ఇన్ ప్యారల్ విత్ 100 ohms, దట్ ఇస్ నథింగ్ బట్ 100 ohms దగ్గర V0 అని వస్తుంది. నౌ అప్లయింగ్ 10 amperes minus 8 amperes equal 2 amperes. R equal to 25 into 20 by 45, that equal to 11.11 ohms. So V0 equal to 2 into 11.11 by 100 plus 11.11 into 100, that equal to V0 equal to 20 volts వస్తుంది. ఇప్పుడు నార్మల్గా 250 volts అని వేసేసి సేమ్ డయాగ్రామ్ తీసుకుంటే కరెంట్ త్రూ 250 volts source is I equal to 250 by 5 plus 250 minus 20 by 25, that equal to I equal to 59.2 amperes. Power supplied by 250 volts is 250 into 59.2, that equal 14,800 watts, that equal 14.8k watts. An electrical load absorbs an average power of 85 kilowatts at lagging power factor of 0.85. If the load operates at 240 volts RMS, calculate the complex power and impedance of the load. Solution given P equal to 85 kilowatt, cos phi equal to 0.85 lagging, Vrms equal to 240 volts, S bar equal to how much, Z equal to how much, P equal to Vrms into Irms into cos phi. P means 85 into 10 cube equal to 240 into Irms into 0.85. Irms equal to 416.67 A. Cos phi equal to 0.85. Phi equal to cos inverse of 0.85. Phi equal to 31.788. Reactive power Q equal to Vrms into Irms sin phi. That equal to 240 into 416.67 into sin 31.788. That equal to 5268.2 VAR. 52.678 kilo VAR. S bar equal to P bar plus J Q bar. S bar equal to 85 plus J 52.678 kilovolt amperes. Load Z equal to Vrms by Irms. That equal to 240 by 416.67. That equal to 0.49 plus 0.303 ohms. Draw the neat sketch of the edge and screw dislocations. Illustrate the Burgers vector on the sketches of dislocations. Then the Burgers vector is always edge location, screw dislocation, the arrows. Next question is calculate the line energy of dislocation in BCC iron if the shear modulus and lattice parameter of BCC iron are 80.2 Gn per meter square and 2.87 angstroms respectively. Then line energy of dislocation equal half Gb square, where G is the shear modulus and B is the magnitude of Burgers vector. B equal to K by 2 half A square plus B square plus C square whole power 1 by 2. That can be read as K numerator part K into root over A square plus B square plus C square whole by 2. B equal to, for the given question, capital G equal to 80.2 into 10 power 19 newtons per meter square, capital K equal to 2.87 angstrom units, A equal to B equal to C equal to 1, then B equal to 2.87 by 2 into 10 power minus 10 into 1 square plus 1 square plus 1 square whole power 1 by 2, that equal to 2.485 into 10 power minus 10. Line energy of dislocation equal to half Gb square equal to half of 80.2 into 10 power 9 into 2.485 into 10 power minus 10 whole square, that equal 2.476 into 10 power minus 9 joules per meter. A PN junction solar cell is fabricated using silicon and has the following important parameters: Na equal to 3 into 10 power 18 per centimeter cube, Nd equal to 2 into 10 power 16 per centimeter cube, Dn equal to 25 centimeter square per second, Dp equal to 10 centimeter square per second, tau n naught equal to 4 into 10 power minus 7 second, tau p naught equal to 10 power minus 7 second. The photocurrent density JL equal to 20 milliamperes per centimeter square. Calculate the open circuit voltage of the solar cell at T equal to 300K. Assume Ni equal to 1.5 into 10 power 10 per centimeter cube. Reverse saturation current density Js equal to QdP Px naught by Lp plus Qdn Np naught by Ln. That equal to QdP Ni square by NdLp plus Qdn Ni square by NaLn, where Lp equal to root over dp tau p, that equal to root over 10 into 10 power minus 7, that equal to 10 power minus 3 centimeters. Ln equal to root over dn tau n, that equal to root over 25 into 4 into 10 power minus 7, that equal to 3.16 into 10 power minus 3 centimeters. So Js equal to 1.6 into 10 power minus 19 into 1.5 into 10 power 10 whole square into 10 by 10 power minus 3 into 2 into 10 power 16 plus 25 by 3.16 into 10 power minus 3 into 3 into 10 power 16. Js equal to 2.7493 into 10 power minus 11 ampere per centimeter square. Open circuit voltage VOC equal to VT natural log of 1 plus 1 and separate to plus and separate to JC by JS, that equal 0.026 natural log of 1 plus JC 20 into 10 power minus 3 by 2.7493 into 10 power minus 11. VOC equal to 0.7101 volts. What are the two functions of commutator in DC machines? The commutator in DC machines has multiple functions, including converting AC to DC in a DC generator. The commutator converts alternating current AC into DC In a DC motor, the commutator converts DC to AC, collecting and supplying current. The commutator collects current from the armature conductor and supply it to the load using brushes, ensuring one directional current. The commutator ensures that the current from the generator always flows in one direction, providing unidirectional torque. In a DC motor, the commutator also provides unidirectional torque. A commutator is an essential component in electric motors, generators, and dynamometers. Its primary function is to reverse the direction of current flow in the windings of the machine. This ensures continuous rotation in one direction in motors and converts alternating current to DC current in generators. As the armature rotates within the magnetic field, the commutator segments periodically changes their connection to the brushes. This reverses the current flowing through the armature coils, maintaining continuous rotation in one direction in motors. In generators, the commutator converts the alternating current induced in the armature coils into direct current. Explain why end-centered tetragonal geometry does not exist in Bravais crystal structures. Explain why end-centered tetragonal geometry does not exist in Bravais crystal structures. 10 marks. Tetragonal have single four-fold axis symmetry, that is, by 90 degrees rotation around vertical axis you will get same lattice structure. You can understand this by drawing two tetragonal end-centered unit cells side by side. If you joined all four end-centered lattice points to common lattice points of unit cells, points joining two unit cells bracket new unit cells formed will again have single four-fold axis symmetry, and as you can observe there is primitive tetragonal again. Hence, due to symmetry, there is no end-centered unit cell. Out of 28 possible lattices or unit cells, there are 14 which are not mentioned in the Bravais lattice because of same reason, symmetry. Next question is, differentiate between different types of magnetic materials on the basis of magnetic dipoles and hysteresis loops. Material type: diamagnetic. Then in diamagnetic, the magnetic dipoles are in induced align opposite to external field, and in diamagnetic the hysteresis is loop characteristics is no hysteresis loop, linear curve. Paramagnetic magnetic dipoles are permanent, align weakly with external field. Hysteresis in loop characteristics is very narrow loop, weak, reversible. In ferromagnetic magnetic dipoles, permanent, align strongly with external field. The hysteresis loop characteristics is large, broad loop, highly retentivity. Antiferromagnetic magnetic properties: permanent, align in opposite directions, net zero. Hysteresis loop characteristics is very narrow loop, so no net magnetization. In ferrimagnetic magnetic dipoles having permanent, opposite but unequal, net. The hysteresis loop characteristics gives you broad loop, moderately retentivity. Moderates retentivity. Design a Widlar current source shown in the figure below to give I naught equal to 5 microamps and IR equal to 1 milliamps, IR equal to 1 milliamps. The parameters are VCC equal 30 volts, VBE1 equal 0.7 volts, VT equal 26 millivolts, beta F equal to 100. Here the base of the transistor is connected to the ground, okay now, and the connector is given R1 and given VCC, then connected to this base is given one shorted, the emitter is grounded, one more transistor connected, it is having only emitter resistance R2, that's all. That is called the current Widlar circuit. Widlar current source beta equal to 100, which is large beta, hence IB can be neglected. 30 equal to IR into R1 plus VBE1, okay now, that is the loop resistance. Then R1 equal to 30 minus 0.7 by 1 milliamperes, that equal 29.3 kilo ohms. R2 equal to VBE1 minus VBE2 by I naught. VBE1 means VT natural log IR by IS minus VT natural log by I naught by IS whole by I naught. So R2 equal to VT natural log
IR by I naught whole by I naught. So 0.026 natural log 1 into 10 power minus 3 by 5 into 10 power minus 6 whole by 5 into 10 power minus 6. So R2 equal to 27.55 kilo ohms. Next question is, design an amplifier that has a voltage gain of 2 if Vin less than 0 and 1 if Vin greater than 0. Assume ideal diodes and ideal op amps are available. If Vin less than 0, then V0 equal to Vin. If Vin greater than 0, then V0 equal to Vi. Such circuits can be designed by using precision half-wave rectifiers, unity gain inverting amplifiers, and inverting summing amplifier. Okay, now these are the three circuits that can be drawn. Precision half-wave rectifier, one op amp ఉంటుంది, పాజిటివ్ అండ్ గ్రౌండెడ్ ఇస్తాం. నెగిటివ్ టెర్మినల్స్కి ఏమో ఒక డయోడ్ ఇచ్చి దాని అవుట్పుట్లో ఇస్తాం. నెక్స్ట్ దాని యొక్క ఒక డయోడ్ ఇచ్చాం కదా, నెక్స్ట్లో ఇంకొక డయోడ్ వేస్తాం. అట్ ద అవుట్పుట్ అట్ నెగిటివ్ టెర్మినల్ వన్ డయోడ్ వేస్తాం వేర్ ఇట్ ఈస్ కనెక్టెడ్ టు ద అవుట్పుట్. ఓకేనా. నెక్స్ట్ అక్కడ అవుట్పుట్ నుంచి మరొక డయోడ్ వేసుకుంటాం. ఓకేనా. దానిపైన ఒక రెసిస్టెన్స్ వేసుకుంటాం. నెగిటివ్ టు అవుట్పుట్కి ఒక ఆర్ వేసుకుంటాం. నెగిటివ్ టెర్మినల్కి అలాగే ఇన్పుట్లో ఒక ఆర్ వేసుకుంటాం. ఓకేనా. మొత్తం సర్క్యూట్కి ఇంకో రెసిస్టెన్స్ వేసి దానికి మైనస్ టెర్మినల్ ఆఫ్ ద నెక్స్ట్ ఆప్ యాంప్కి ఇస్తాం. దానికి ఒక నెగిటివ్ ఫీడ్బ్యాక్ అనేది ఆర్ అని ఇస్తాం. నెక్స్ట్ పాజిటివ్ గ్రౌండ్కి ఇస్తాం. దీని యొక్క నెగిటివ్ టెర్మినల్ ఆర్కి ఇచ్చి ఇంకో ఆప్ యాంప్ నెగిటివ్ ఫీడ్బ్యాక్ ఆప్ యాంప్ ఆర్ అని వేసుకొని చేస్తాం. దిస్ ఈజ్ ద సర్క్యూట్. ఓకేనా. ఇఫ్ విఎన్ గ్రేటర్ దెన్ 0, విఓఏ ఈక్వల్ టు నెగిటివ్, D1 means off, D2 means on. KCL minus Vin minus 0 by R plus 0 minus 0 by R plus V0 minus 0 by R equal to 0. V0 equal to Vin. VOA equal to positive, that implies D1 on, D2 off. D1 on, D2 off. Like that we have to calculate. Again, if we apply KCL minus Vin minus 0 by R plus minus Vin minus 0 by R plus V0 minus 0 by R equal to 0. V0 equal to 2 times that of Vin. Next question. Discuss the points of similarities between a transformer and induction machine. Explain why an induction machine is called a generalized transformer. Generalized transformer. So the question answer is, an induction machine, often called an induction motor or generator, shares several similarities with a transformer. Here are the key points of similarities and the reasons why an induction motor machine is referred as generalized transformer. Similarities between transformer and induction machine. Electromagnetic induction principle. Both devices operate on the principle of electromagnetic induction. In a transformer, an alternating current is the primary. The primary winding creates a magnetic field that induces a voltage in the secondary winding. Similarly, in an induction machine, an AC current is the stator winding creates a rotating magnetic field that induces a current in the rotor. Core construction. Both transformers and induction machines have a magnetic core made of laminated sheets of silicon steel. This core helps to guide and enhance the magnetic flux and reduces eddy current losses. Windings. Transformers have primary and secondary windings, while induction machines have stator and rotor windings. These windings are essential for the induction process in both devices. Energy conversion. Both transformers and induction machines transfer energy via magnetic fields. In transformers, electrical energy is transferred from one circuit to another, while induction machines, electrical energy is converted into mechanical energy. In motors or vice versa. In brackets lo generators. Frequency of operation. Both typically operate at the same frequency as the input AC supply. For transformers, the output frequency matches the input frequency. For induction machines, the stator frequency is the same as the supply, while the rotor frequency varies depending on slip losses. Both devices experience similar type of losses such as copper losses in windings and core losses in brackets, hysteresis and eddy current losses in the core. Why induction machine is called a generalized transformer? An induction machine is termed as a generalized transformer due to the following reasons. Energy transfer mechanism. Just like a transformer transfers energy from its primary to its secondary winding via magnetic induction. An induction machine transfers energy from the stator acting as a primary winding to the rotor acting as a secondary winding. The major difference is that in an induction machine, the secondary rotor winding is movable and creates mechanical energy related to motion. In a transformer, the windings are stationary and transfer of energy is pure electrical. Induction machine, the relative motion between the stator rotating magnetic field and the rotor induces current in the rotor, leading to the development of torque and mechanical energy. Slip, the concept of slip in induction machines, difference between the synchronous speed of the magnetic field and the actual speed of the rotor adds to their complexity compared to transformers. This slip is analogous to the voltage regulation in transformers, reflecting how effectively the energy transfer takes place. Variable load operation, an induction machine can operate under varying mechanical loads which alters its slips and efficiencies, similar to how a transformer's load affects its voltage regulation and efficiency. This makes induction machines versatile like transformers in handling different types of loads. Next, rotor circuit analogous to secondary windings. In an induction machine, the rotor circuit can be likened to the secondary winding of a transformer, with rotor currents being induced by the stator's rotating magnetic field. This is akin to the secondary voltage induction induced by the primary current in a transformer. Third B question. A 10 kilovolt bar 2500 bar 250 volts single phase transformer has the following parameters: primary winding HV side resistance R1 equal to 2.4 ohms, leakage reactance X1 equal to 6.00 ohms, secondary winding LV side resistance R2 equal to 0.03 ohms, leakage reactance X2 equal to 0.07 ohms. 0.07 ohms. With primary supply voltage held constant at 2500 volts, calculate the secondary terminal voltage when the low voltage winding is connected to a load impedance of 5 plus j 3.5 ohms and the transformer delivers its rated current at 0.8 power factor lagging on the low voltage side. The answer is 10 kVA, 2500 bar, 250 volts, 1 phase transformer HV R1 equal to 2.4 ohms, X1 equal to 6 ohms, whereas compared to LV side R1 equal to 0.03 ohms, X2 equal to 0.07 ohms, primary supply voltage equal to 2500 volts, load equal to 5 plus j 3.5 ohms at 0.8 power factor lagging. Secondary terminal voltage is equal to how much? Circuit references to secondary A equal to 2500 by 250. 2500 by 250, that equal to 10. R equivalent of LV equal to 2.4 by 10 square, that is separate part, plus 0.03 ohms equal to 0.054 ohms. X equivalent of LV side equal to 6 by 10 square is separate, plus 0.07 ohms, that equal to 0.13 ohms. Load equal to 5 plus j into 3.5 ohms, that equal to 6.10 at the angle of 35 degrees. I2 equal to Vt by ZL, Vt by 6.10. Okay, now the equivalent circuit becomes 250 volts is the input voltage, R equivalent comma of LV ఒక రెసిస్టెన్స్ వస్తుంది, I2 కరెంట్ అనేది పాస్ అవుతుంది, X ఈక్వలెంట్ బార్ V అనేది వస్తుంది. ఓకేనా, VT వోల్టేజ్, దాని అవుట్పుట్ రెసిస్టెన్స్ ఏమొస్తుంది అంటే 5 ప్లస్ j 3.5 ohms. 250 ఈక్వల్ టు VT ప్లస్ I2 R ఈక్వలెంట్ LV cos 5 ప్లస్ I2 X ఈక్వలెంట్ LV sin 5. 250 ఈక్వల్ టు VT ప్లస్ VT బై 6.10 హాఫ్ అంటే VT పక్కన వస్తుంది హాఫ్ 0.054 ఇంటూ 0.8 ప్లస్ 0.13 ఇంటూ 0.6. 250 ఈక్వల్ టు VT ప్లస్ VT ఇంటూ 0.0198. VT ఈక్వల్ టు 250 బై 1.0198, that equal 245.146 volts. Thirdly, C. Discuss photoelectric effect and find out the number of photoelectrons emitted per unit time from a transmitter operated at a frequency of 800 kHz and 10 kilowatt power 10 marks. Power equal to 10 kilowatt, that equal 10 kJ per second. Frequency F equal to 800 kHz. Energy of photon equal HF equal to 6.63 into 10 power minus 34 into 800 into 10 power 3 joules, that equal 5.304 in 10 power minus 28 joules. Number of photoelectrons emitted per second equal to 10 into 10 cube whole by 5.304 into 10 power minus 28, that equal to 1.88 into 10 power 31 per second. Next question is, define dielectric strength. Discuss different types of dielectric breakdowns in solids. Dielectric strength is defined as the maximum voltage required to produce a dielectric breakdown through the material and is expressed as volts per unit thickness. The higher the dielectric strength of a material, the better its quality as an insulator. Breakdown mechanism varies depending on the time of applications of voltage and is classified as intrinsic or ionic breakdown, electronic mechanical breakdown, thermal breakdown, electrochemical breakdown, treeing and tracking, internal discharges. ఓకేనా. బ్రేక్డౌన్ అనేది y యాక్సిస్, x యాక్సిస్ లాగ్ టైమ్ అని వేసుకుంటే దెన్ యూ విల్ గెట్ ఎరోజన్ అండ్ ఎలక్ట్రోకెమికల్ అనేది థర్మల్, స్ట్రీమర్, ఇంట్రిన్సిక్, ఎలక్ట్రోమెకానికల్, ఇంట్రిన్సిక్ బ్రేక్డౌన్ అండ్ ఆల్ దీస్ బ్రేక్డౌన్స్ ఆర్ వెరీ వెరీ ఇంపార్టెంట్. నెక్స్ట్ ఎలక్ట్రానిక్ బ్రేక్డౌన్, అవలాంచ్ ఆర్ స్ట్రీమర్ breakdown due to treeing and tracking. When solid dielectric is subjected to electrical stresses for a long time, two kinds of visible markings are observed: presence of conducting path mechanisms whereby leakage current passes through the conducting path, finally leading to the formation of spark, spreading of spark channels during tracking in the form of branches of a tree called treeing. In practice, the surface of solid dielectric material always having the conducting film which is formed due to moisture. On approach of voltage, the film starts conducting, resulting in generation of heat, and the surface starts becoming dry. The conducting film becomes separate or due to drying, and so sparks are drawn from damaging. Electromechanical breakdown failures occurs due to electrostatic compressive forces which can exceed the mechanical compressive strength. If the thickness of specimen d0 and is expressed to the thickness under d under n applied voltage V, the highest apparent electric stress before breakdown is E max equal to V by d0 equal to 0.5 into separate వస్తుంది root over y by epsilon naught epsilon r, where y means Young's modulus. Mechanical instability occurs when d by d0 equals 0.6. Next question, for the circuit shown in the figure below, determine the frequency of oscillations f0 and overall voltage gain AV, and also identify the type of oscillator. Assume op amps are ideal. ఎలా అంటే ఒక ఆప్ యాంప్లో నెగిటివ్ టెర్మినల్కి నెగిటివ్ ఫీడ్బ్యాక్ 1 మైక్రోఫారడ్స్ కెపాసిటర్ వేస్తాం. ఆ నెగిటివ్ టెర్మినల్కి 1 కిలో ఓమ్స్ ఇచ్చేసి షార్ట్ చేస్తాం. ఓకేనా. దాని ఒక అవుట్పుట్కి 1 కిలో ఓమ్స్ ఇస్తాం. ఆ అవుట్పుట్ నుంచి ఇంకో ఆప్ యాంప్కి ఇచ్చి నెగిటివ్ టెర్మినల్కి ఇస్తాం. దాని యొక్క నెగిటివ్ ఫీడ్బ్యాక్ 1 మైక్రోఫారడ్స్ ఇస్తాం. ఫస్ట్ యొక్క ఆప్ యాంప్కి పాజిటివ్ ఫీడ్బ్యాక్లో ఒక కెపాసిటర్ గ్రౌండ్ చేసి ఒక 1 kV అనేది సెకండ్ ఆప్ యాంప్ యొక్క అవుట్పుట్కి ఇస్తాం. దిస్ ఈజ్ ద సర్క్యూట్ డయాగ్రామ్. ద సొల్యూషన్ ఈజ్ గివెన్ సర్క్యూట్ ఈజ్ కాల్డ్ as quadrature oscillator. VON is a sine wave and V2 is a cos wave analysis. It is a cos wave. Then VO2 equal to minus 1 by SC by R into VON, that equal to minus VON by SC SRC. For A1, V plus equal to V02 by SC whole by R plus 1 by SC, R separate to 1 by SC separate, that equal to V02 by 1 plus SRC, that equal to minus V01 by SRC into 1 plus SRC. V01 dash equal to 1 plus 1 by SC whole by R into V plus V01 dash equal to 1 plus 1 by SRC into V0 minus V01 by SRC of 1 plus SRC. SRC of 1 plus SRC in the denominator part. Loop gain V0 dash 1 by V01 equal to 1 plus SRC into minus 1 at numerator part. Denominator part SRC into 1 plus SRC. That is nothing but loop gain equal to minus 1 by S square R square C square. Put S equal j omega. Loop gain equal to 1 by omega square R square C square. Put omega equal to omega naught. Loop gain equal to 1. That implies 1 by omega naught square R square C square equal to 1. Equate to 1 చేస్తే నీకు omega naught equal to 1 by RC or F naught equal to 1 by 2 pi RC. given R equal to 1 kilo ohms, C equal to 1 microfarad, F naught equal to 1 by 2 pi into 10 cube into 10 power minus 6, that equal to 159.15 Hz.
Determine, next question, 4th B. Determine the impedance ZL that results in maximum average power transfer to ZL for the circuit shown in the figure. Calculate the maximum average power transfer to the load impedance determined. Input voltage is 20 angle of 0 degrees. Voltage is connected in series with 5 ohms. Then 5 ohms ki 20 volts ki parallel with 20 ohms. Again series with J3 ohms. Again parallel minus J6 ohms. Again parallel ZL AB. The condition for maximum power transfer in the circuit is ZL equals ZTH conjugate. So we can write it as 5 ohms parallel with 20 ohms in series with J3 ohms in parallel with minus J6 ohms. That is nothing but Z Thevenin's. Z Thevenin's equal to 5 parallel 20 plus J3 whole parallel minus J6. ZTH equal to 4 plus J3 into minus J6 whole by 4 plus J3 minus J6. 5.76 minus J into 1.68 ohms. ZL equal to ZTH bar equal to 5.76 plus J into 1.68 ohms. Calculation of VTH. Voltage source 20 ohms, 20 volts at the angle of 0 degrees. Nothing but DC. No, that is AC. 5 ohms is in series with 5 ohms parallel with 20 ohms in series with J3 ohms parallel with minus J6 ohms. Where TH between AB terminals, then equivalent Thevenin's equivalent circuit is VAB equal 20 into 20 by 25, that equals 16 volts. RTH equal 5 into 20 by 25, that equals 4 ohms. Next 16 volts in series with 4 ohms in series with J3 ohms in parallel with minus J6 ohms, that is VTH. VTH equal to 16 into minus J6 whole by 4 plus J3 minus J6. 4 plus J3 minus J6 is the denominator part, that equal 19.2 into angle of minus 53.13 degrees volts. Then now the circuit is 19.2 at the angle of minus 53.13 volts. ZTH series in series with ZL. P max equal to VTH square by 4 R2, that equal to 19.2 into 19.2 whole by 4 into 5.76, that equal to 16 watts. What are the major factors that have led to acceleration and development of solar and wind power? Solar and wind power. The acceleration and development of solar and wind power have been driven by combination of technological advancements, economical factors, policy measures, and social hint shifts. Here are the major factors: technological advancement, improving efficiency, cost reductions, energy storage, grid integration. Economic factors: declining costs, investment and financing, job creation, policy and regulatory support, government incentives, renewable portfolio standards. Environment and social factors: climate change awareness, energy independence, public support, global trends and agreements, international agreements, corporate commitments, urbanization, electrification, economic competitiveness, price competitiveness, grid parity. Next, fourth row C. To produce a p-type semiconductor, the boron is doped in pure silicon. Doping is done through the B2O3 vapor phase of a surface concentration equivalent to 3.3 into 10 power 26 boron atoms per meter cube. Calculate the time required to get a boron content of 10 power 23 atoms per meter cube at a depth of 2 micrometers. The doping temperature is 1000 degrees centigrade and dB in silicon at this temperature is 4 in 10 power minus 17 meters square per second. Given ERF of 0.95 equal to 0.8209, ERF of 1.0 equal to 0.8427, ERF of 2.4 equal to 0.9993, ERF of 2.6 equal to 0.9998. Surface concentration N0 equal to 3.3 in 10 power 26 boron atoms per meter cube. NB equal to 10 power 23 atoms per meter cube. XJ equal to 2 micrometers. DB equal to 4 in 10 power minus 17 meters square per second. We know N of x comma t equal to N0 of ERFC of x by 2 root delta dt, where x is the numerator part, 2 root dt is the denominator part, 2 into root over dt. Once again repeat, N of x comma t equal to N0 into ERFC of x by 2 root dt, that equal to 10 power 23 equal to 3.3 in 10 power 26 ERFC of numerator power 2 into 10 power minus 6 by denominator power 2 into root of 4 into 10 power minus 17 into t. Then 3 into 0.3 into 10 power minus 4 equal to ERFC of 10 power minus 6 whole by root over 4 into 10 power minus 17 into t. So ERFC of x equal to 1 minus ER of x. ERFC of x equal to 1 minus ER of x, that equal 3 into 0.3 into 10 power minus 4 equal to 1 minus ERF of 10 power minus 6 whole by 4 into root over 4 into 10 power minus 17 into t. ERF whole inverse of 0.9999697 equal to 10 power minus 6 whole by root over 4 into 10 power minus 17 into t from given data. ERF of 2.6 equal to 0.9998. 2.6 equal to ERF inverse of 0.9998. 2.6 equal to 10 power minus 6 by root of 4 and 10 power minus 17 into t. Therefore, the value of t can be obtained as 1.02 hours. 1.02 hours. Assume an ideal 10-bit ADC with V reference equal to 5 volts is used to sample 1 volt peak-to-peak sinusoidal signal that has a 2.5 volt offset. What percentage of error can be expected in the peak voltage measurement due to quantization of effect of the ADC? The error is related to the magnitude of the sinusoid. Step 1. Determine the ADC resolution. A 10-bit ADC has 2 power 10 equal to 1024 discrete levels with a reference voltage V reference of 5 volts. The voltage range from 0 to 5 volts is divided into 1024 levels. The voltage corresponding to each discrete level, in brackets the quantization steps, is given by delta equal to V reference by 2 power n, that equal to 5 by 1024, that is approximately equal to 0.00488 volts. Step 2. Quantization error. The maximum quantization error is EQ for an ideal ADC is half of the quantization step size. This represents the maximum deviation that the actual analog value can have from the quantized digital value. EQ equal to delta V by 2, that equal to 0.00488 by 2, that is nearly equal to 0.00244 volts. Determine the magnitude of the sinusoidal signal. The given sinusoidal signal has peak-to-peak value of 1 volt and offset of 2.5. This means the signal varies from 2.5 minus 0.5 equal to 2 volts to 2.5 plus 0.5 equal to 3 volts. The magnitude of sinusoid, the peak amplitude from the center line, is half of the peak-to-peak value. A equal to half V, that equals 0.5 V. Calculate the percentage error. To find the percentage error in the peak voltage measurement due to quantization, we compare the maximum quantization error to the magnitude of the sinusoidal signal. Percent error equal to EQ by A into 100%. Substituting the known values, percentage error equal to 0.000244 by 0.5 into 100%, that gives you 0.488%. The percentage error in the peak voltage measurement due to quantization effect of the ADC is approximately 0.488%. This error arises because the ADC can only represent the analog input within discrete steps, leading to a small but inevitable deviation between the actual analog value and the quantized digital value. Fifth law B. A 555 IC is connected as shown in the figure below. Determine the frequency of oscillation and the duty cycle. Assume that diode is an ideal op-amp. Ideal diode. Nothing but ఒక డబ్బా గీస్తాం, కిందేమో 1.5 వస్తుంది, పైనేమో 8.4 వస్తుంది. 1కేమో ఒక కెపాసిటర్ వేస్తాం, 5 ఒక కెపాసిటర్ షార్ట్ చేసేసి ఇంకో కెపాసిటర్ వేసేసి 2.6 షార్ట్ చేస్తాం. ఆ 2.6 నుంచి ఒక దానికి నెగిటివ్ క్యాథోడ్ డయోడ్ వేసి 7 కలెక్ట్ చేస్తాం. ఓకేనా, 7కి 2.6కి మధ్యలో ఒక 10 కిలో ఓమ్స్ వేస్తాం. ఇంకో 7కి 8.4కి మధ్యలో 10 కిలో ఓమ్స్ వేస్తాం. 10 కిలో ఓమ్స్ వేస్తాం కదా, వీసీసీ అనేది 8కి 4కి వేస్తాం. 3 దగ్గర అవుట్పుట్ చేస్తాం V0. Given circuit is stable multivibrator, it provides a square wave output. T high equal to 0.69 into RAC, that equals 0.69 into 10 power 4 into 10 power minus 8. T high equals 69 microseconds. T low equal to 0.69 RBC, that equals 0.69 into 10 power 4 into 10 power minus 8. T low equal to 69 microseconds. Time period T0 equal to T high plus T low. T0 equal to 138 microseconds. Frequency of output is F0 equal to 1 by T0, that equals 7.246 kilohertz. duty cycle of output equal to T high by T naught into 100%, that equals 69 by 138 into 100%, that equal to 50%. The network of the figure contains both a dependent voltage source and a dependent current source. Determine the Y and Z. ఓకేనా, ప్లస్ మైనస్ దగ్గర 1 ohms అనేది ప్లస్ మైనస్ మధ్యలో ఉంటుంది. ద 1 ohms ఇస్ ప్యారల్ విత్ 2V2 అప్వర్డ్ కరెంట్. ఓకేనా, ద 2V2 ఈజ్ ఇన్ సిరీస్ విత్ 1 ohms ఈజ్ ఇన్ సిరీస్ విత్ మైనస్ ప్లస్ 2V1 ఈజ్ ఇన్ ప్యారల్ విత్ 2 ohms. ద 2 ohms అవుట్పుట్ V2. ఓకేనా, ఫర్ దిస్ అప్లై KCL at V1. At V1 you apply KCL, then you will get I1 plus 2V2 equal to V1 plus 2V1 minus V2 whole by 1 plus V1 by 1. I1 equal 4V1 minus 3V2. Apply KCL at V2 dash. I2 equal to V2 minus 2V1 minus V1 whole by 1 plus V2 by 2. I1 equal to minus 3V1 plus 3 by 2 V2. Y parameters equation. I1 equal to Y11 V1 plus Y12 V2. Y2 equal to Y21 V1 plus Y22 V2. Comparing equations 1 and 2 and 4, then you will get to Y parameters. Z parameters equal to 1 by 4 into 3 by 2 minus 9, AD minus BA, 3 by 2, 3, 3, 4. Okay, na. Z equal to minus 1 by 3 of 3 by 2, 3, 3, 4, that equal to 1 by minus 1 by 2 minus 1 minus 1 minus 4 by 3. At t equal to 0 minus, the capacitor reaches to steady states and acts as a open circuit. The actual question is in the figure shown. A network with a steady state is reached with a switch K open at t equal to 0. The switch is closed. For the element values given, determine the value of VA 0 minus and VA 0 plus. The circuit is the ఏమీ లేదు, పైన 10 ohms వస్తుంది. ఓకేనా, దాని దగ్గర కింద 10 ohms పక్కన 20 ohms వస్తుంది. దాని 10 ohmsకి 20 ohms మధ్యలో VA వచ్చి అక్కడ స్విచ్ వచ్చి అక్కడ 10 ohms వచ్చి గ్రౌండ్ అయిపోతుంది. ఓకేనా, ఈ లెఫ్ట్ సైడ్ అక్కడ 10 ohmsకి 5 volts వస్తుంది, రైట్ సైడ్ అక్కడ 20 ohmsకి 2 farads వచ్చి షార్ట్ అయిపోతుంది. దట్ ఈస్ ద డయాగ్రామ్. అప్లైయింగ్ KCL at V1 means I1 plus 2V2 equal to V1 plus 2V1 minus V2 by 1 plus V1 by 1. I1 equal 4V1 minus 3V2. Apply KCL like that చేస్తే రాదు కానీ at t equal 0 minus the capacitor reaches to steady state and it acts as open circuit. ఓకేనా, open circuit VA of 0 minus equal to 5 volts. That equal to VAB of 0 minus equal to 5 volts. T equal to 0 plus అప్పుడు ఆ 10 ohms అనేది మధ్యలో వస్తుంది. VF 0 plus minus 5 by 10 plus VF 0 plus minus 5 by 20 plus VF 0 plus by 10 equal to 0. Then మీకు సాల్వ్ చేస్తే VF 0 plus equal to 3 volts. ఫిఫ్త్లో D. For the figure shown, how is the figure means 2 voltsకి సిరీస్ విత్ హాఫ్ ohms. ఓకేనా, దానికి ప్యారల్ విత్ 1 ohms, సిరీస్ విత్ 1 ohms. ఆ 1 ohmsకి 2 voltsకి ప్యారల్ విత్ హాఫ్ ohms, ఆ ప్యారల్ విత్ 1 amperes. 1 ampereకి సిరీస్ విత్ 1 ohms, ఆ 1 ohmsకి ప్యారల్ విత్ 1 ohms, ఆ 1 ohmsకి ప్యారల్ విత్ 2 volts వోల్టేజ్ సోర్స్. ఓకేనా, దెన్ 1 ohmsకి 2 ohms ప్యారల్ వస్తుంది. అప్లైయింగ్ KCL at V1 gives you 2 of V1 minus 2 plus V1 minus 2 V2 by 1 plus V1 minus 2 by 2. Then you will get 7 V1 minus 2 V2 equal to 10. Apply KCL at V2. 2 V2 plus V2 minus V1 plus V2 minus 2 equal to 1. Then V1 equal to 1.7629, V2 equal to 1.192, I1 equal to V1 minus V2. That implies 0.5709 amps. Next question. The network conductors in shown figure. ఒక క్యూబాయిడ్లో అన్నిటికీ ఇండక్టర్స్ వేస్తాం. is composed of 1 Henry inductor on each edge of a cube with the inductors connected to the vertices of the cubes as shown. Find out the L equivalent between the terminals A, B. Diagonal terminals ఉంటాయి కదా, A, B దగ్గర ఎంత అని అడిగాడు. Simply you connect on a voltage source V. Then V equal to L into di by dt. Then there is the formula So everywhere you will get the I by 3 current. Next L by 6 current. V equal to L into d by dt of I by 3 plus L into d by dt of 1 by 6 plus L into d by dt of I by 3. Solve చేస్తే V by dl by dt equal to L into 1 by 3 plus 1 by 6 plus 1 by 3. L AB equal to 5 by 6. L equivalent equal to 5 by 6 henries. 5 by 6 henries. 5 లో E. It is desired to measure the voltage across the 50 kilo ohms resistor. The circuit shown in the figure. 2 voltmeters are available for this measurement. Voltmeter 1 with sensitivity of 1000 ohms per volt and voltmeter 2 with sensitivity of 20,000 volts per mole. Both meters are used on their 50 volt range. Calculate the reading of each meter. Circuit is 150 volts input ఇచ్చి దాని సిరీస్ విత్ 100 కిలో ఓమ్స్ ఇచ్చి ఇన్ సిరీస్ విత్ 50 కిలో ఓమ్స్. ఆ 50 కిలో ఓమ్స్కి ప్యారల్గా వోల్టేజ్ V పెట్టాం. గివెన్ సెన్సిటివిటీ ఆఫ్ వోల్ట్మీటర్ ఈక్వల్ టు 1, SV1 ఈక్వల్ టు 1000 ohms per volt, SV2 ఈక్వల్ టు 20,000 ohms per volt. Full scale voltage using ohm meter VFX equal to 50 volts. ఓకేనా. That RV1 be the internal resistance of voltmeter. RV1 equal to SV1 into VFS, that equal to 100 into 50, that equal 50 kilometers. Reading of voltmeter 1, V1 equal to 150 into R dash by R dash plus 100 kilo ohms. R dash equal to 150 kilo ohms parallel with RV1, that equal 50 kilo ohms parallel with 50 kilo ohms, 25 kilo ohms. V1 equal to 150 into 25 by 25 plus 100, that equal to 30 volts. Using voltmeter 2, same. RV2 is nothing but SV2 into VFS, that equal 20,000 into 50, that is equal to 1000 kilo ohms. Reading of voltmeter 2 equal to 150 into R dash by R dash plus 100 kilo ohms, where R double dash equal 47.62 kilo ohms. V2 equal to 48.38 volts. Question number 6a. For the circuit shown in the figure below, MOS and BJT are operating in saturation and active mode respectively. The capacitor C is very large, Vm is small. The parameters of the transistor are μn CoX equal to 100 milliamperes per volt square, Vtn equal to 1 volt, L equal to 2 micrometers, Vt equal to 25 millivolts, beta F equal to 100, Vb equal to 0.7 volts. Said quotient output voltage is 5 volts. Size of the MOSFET and calculate small voltage gain AV equal to VOW by Vs. VOW by Vs. Nothing but we have voltage source Vs equal to Vm sin omega t plus 5 in series with C. అక్కడ నుంచి ఒక రెసిస్టర్ 400 కిలో ఓమ్స్ పైకి పోయి ఇంకోటి డైరెక్ట్గా ఒక బీజేటీకి పోతుంది. ఆ బీజేటీ నుంచి కనెక్టర్ టు సోర్స్ ఆఫ్ ద MOSFET is connected, and then gate to 400 kilo ohms is shorted, and M2 of the drain is shorted to VDD of 10 volts. Output is taken between M2 and Q1, that is the collector of the transistor to emitter source of the MOSFET. The output Vout is taken. For DC analysis, IB equal to 10 minus VBE by 400K. IB equal to 23.25 microamperes, IC equal to beta IB, that equal to 2.325 milliamperes, IDS equal to IC equal to 2.325 milliamperes, VDS equal to 10 minus 5, that equal to 5 volts. 10 minus 5, that equal to 5 volts, because output is given as quiescent output voltage is given as 5 volts. Now gate is shorted to drain, hence VGS equal to VDS equal to how much? 5 volts. IDS equal to μn CoX by 2 into W by L into VGS minus VT whole square. Then 2.325 into 10 power minus 3 equal to 100 into 10 power minus 6 by 2 into W by L into 5 minus 1 whole square. W by L equal 2.90625. W equal 2.90625 into 2. W equal 5.8125 micrometers. For AC analysis, the common source amplifier or MOSFET where gate is shorted to drain can be written as for equivalent R equivalent equal to 1 by GM2. GM2 equal to μn CoX W by L VGS minus VT, that equal to 1.1625 this one m ohms. R equivalent equal to 1 by GM2 that equal to 860.2 that equal to 0.86 kilo ohms. GM for BJT, GM1 equal to IC by VT that equal to 3.325 milliamps by 25 millivolts. These are all comes under for AC analysis. GM1 equal to 93 milliohms, millimos. Replacing a BJT with pi model. VS 400K, VS ki parallel with 400K will parallel with V pi R pi model. ఓకేనా, దాని పక్కన GM V pi current car traveling to earth, then parallel with in series with R equivalent equal 0.86 kilo ohms. AV equal to V0 by Vs equal to minus GM V pi into R equivalent by V pi that equal to minus GM1 into R equivalent equal to minus 93 into 0.86 that equal to minus 80 ohms. Prove that true power equal to cos phi by cos phi into cos phi minus beta into actual wattmeter reading for electrodynamometer type of wattmeters, where cos phi equal to power factor of the circuit, B equal tan inverse omega L by R, where L and R are the inductance and resistance of the pressure coil of the circuit. Next question, explain why errors are large when the power factor is low. Case when pressure coil is highly resistive, no inductance presence, developed torque, then the phasor diagram is IP ki kindana phi and vachesi IC equal to I, TD equal to I1 I2 cos alpha dm by d theta, that equal to IC IP cos phi dm by d theta, TD equal to I into V by RP cos phi dm by d theta, TD is directly proportional to PT is directly proportional to VI cos phi, true power equal to PT equal to VI cos phi. When pressure coil have inductance where tan beta equal to omega LP by RP, developed torque TD is directly proportional to IP IC cos alpha dm by d theta. Phasor diagram V, ఓకేనా, దాని కింద బీటా ఎస్ ఐపీ, దాని కింద ఫై, దాని ఫై మైనస్ బీటా అని వస్తుంది. వీకి ఐపీకి బీటా, వీకి ఐసీకి ఫై, ఐపీకి ఐసీకి ఫై మైనస్ బీటా, ఐసీ ఈక్వల్ టు ఐ. డెవలప్డ్ టార్క్ టీడీ డైరెక్ట్లీ ప్రొపోర్షనల్ టు టీపీ ఐసీ కాస్ ఆల్ఫా డిఎం బై డి టీటా, డైరెక్ట్లీ ప్రొపోర్షనల్ టు టీపీ ఐపీ ఐసీ కాస్ ఫై మైనస్ బీటా డిఎం బై డి టీటా, డైరెక్ట్లీ ప్రొపోర్షనల్ టు వి బై ఆర్పీ ఐ కాస్ ఫై మైనస్ బీటా టు డిఎం బై డి టీటా. So TD is directly proportional to VI cos beta cos phi minus beta into dm by z into d theta, cos beta equal to rp by z. Measured power Pm equal to VI cos beta cos of phi minus beta. The correction factor Cf equal to time power by measured power that equal to V2 cos y, V2 cos beta into cos of phi minus beta. So true power equal to cos phi by cos beta into cos phi minus beta into measured power. Reasons for large errors at power factor: increased phase angle errors, voltage and current phase displacement. At low power factors, the phase angle phi between voltage and current is large. Measurement instruments, especially older or less sophisticated ones, can struggle to accurately determine the exact phase angle, leading to significant errors in calculating real power. Instrumentation accuracy: instruments like wattmeters and power meters are more prone to phase angle errors when the power factor is low, because the real power factor component becomes a smaller fraction of the total apparent power. Thus any error in the phase angle measurement can cause disproportionate error in real power calculation. High sensitivity to measurement noise impact: measurement system can pick up electrical noise and distortions when the power factor is low. The real power signal, which is small, can be easily masked by noise, leading to inaccuracy. Signal to noise ratio: with low power factor, the signal to noise ratio decreases for the real power measurements, making the systems more sensitive to external disturbances and measurements inaccuracies. Increased impact of harmonics and distortions. Low power factor systems often experience increased harmonics, especially non-linear loads. Harmonics causes deviations from the ideal sinusoidal waveforms, making accurate measurement and analysis more challenging. Effect on power quality: harmonics can distort voltage and current waveforms, leading to errors in power calculations and reducing the accuracy of power factor correction equipment. Reactive power dominance: high reactive power. At low power factors, the system has high reactive power, which does not contribute to real work but still influences the total current. Measuring instruments may misinterpret the reactive component after affecting the real power calculation. Apparent power calculation: since apparent power includes both real and reactive power, a higher proportion of reactive power leads to a larger discrepancy between real and apparent power. Cause accurately measurement of real power becomes more challenging as the real power component is relatively small. Accuracy of instrumentation, instrument error characteristics, calibration, linearization, measurement of small real power, proportional error increase. Find the Thevenin equivalent circuit for the terminals A, B. ఎలాగంటే voltage source 100 volts, the angle of 0 degrees V plus or minus. ఓకేనా, దానికి టీ ఫామ్లో ఉంటుంది. టీలో లెఫ్ట్ సైడ్ ఏమో 200 ohms, రైట్ సైడ్ ఏమో J 100 ohms. టీలో మధ్యలోదేమో 100 యాంగిల్ ఆఫ్ 90 degrees V. టీలో పైన బార్ ఉంది కదా, పైన హారిజెంటల్ బార్ ఉంది కదా, దానికి ప్యారలల్గా -J 300 ohms. ఓకేనా, J 100 ohmsకి గ్రౌండ్కి మధ్యలో AB. ఓకేనా, మధ్యలో AB. సో అప్లయింగ్ KCL అట్ VTH నోడ్. VTH అంటే AB ఉంది కదా, VTH మైనస్ 100 యాంగిల్ ఆఫ్ 90 degrees బై J 100 ప్లస్ VTH మైనస్ 100 యాంగిల్ ఆఫ్ 0 degrees మైనస్ J 300 ఈక్వల్ టు 0. ఓకేనా, సాల్వింగ్ దట్ ఈక్వేషన్ యూ విల్ గెట్ VTH ఈక్వల్ 158.03 యాంగిల్ ఆఫ్ 108.43 degrees. ZTH ఈక్వల్ టు J 100 parallel with minus J 300. J 100 is parallel with minus J 300. So ZTH equal to J 150 ohms. Second question, for the ladder network determine the G parameters in the S domain. For the ladder network determine the G parameters in the S domain. We can write it as what the circuit is. Basic circuit given is like this. 1 Henry inductance, okay na, is parallel with 1 ohms, is series with 1 Henry, is parallel with 1 ohms. That means 1 Henry T తీసుకుంటే left side 1 Henry, right side 1 Henry, మధ్యలో 1 ohms. ఓకే నా, నెక్స్ట్ రైట్ సైడ్ 1 ohmsకి parallel with 1 ohms అక్కడ మనం తీసుకున్నాం. దట్ ఇస్ ద ladder network. For this ladder network we will calculate as inductance as S omega, S ohms. ఓకేనా, resistance as 1 ohms. Then I1 equal to G11 V1 plus G12 V2. VT equal to G21 V1 plus GT2 VI2. G11 equal to I2 by V1, that equal to I2 equal to 0 for I2 equal to 0. Then V1 by I1 equal to Zn equal to S plus 1 by S plus 2 plus S. That implies S square plus 3S plus 1. The equivalent circuit becomes like this. I1 అనేది ఇన్పుట్ కరెంట్, V1 అవుట్పుట్ కరెంట్, I2 equal to 0, అవుట్పుట్ వోల్టేజ్ V2. సో G11 equal to I1 by V1 equal to S plus 2 by S square plus 3S plus 1. G21 equal to V2 by V1, I2 equal to 0, VAB equal to V1 into 1 by S, ZAB equal to S by S plus 1. V2 equal to VAB into 1 by S plus 1 plus S by S plus 1. S1 and numerator part, denominator S plus 1 plus 1, S by S plus 1. V2 like that we will calculate. V2 by I2 equal to Z equal to S by S plus 1 plus S parallel 1. Like that we calculate all the S parameters, all G parameters. The parameters of the amplifier shown in the figure below are RC1 equal 4 kilo ohms, RE equal 2 ohms, RC2 equal 5 kilo ohms, RF equal 4 kilo ohms, and RS equal 200 ohms. The DC bias currents of the transistor are IC1 equal to 0.5 milliamperes, IC2 equal to 1 milliampere. Transistor parameters HFE1 equal to HFE2 equal to 150. Use the techniques of feedback analysis to calculate the input resistance RIF, the output resistance RYF, and closed loop trans resistance gain AF. Assume VT equal to 25 millivolts. See, transistor లో బేస్ కేమో 200 ohms అండ్ వోల్టేజ్ సోర్స్ VS ఇస్తాం. ఎమిటర్కి ఏమో RG 2 kilo ohms ఇస్తాం. కలెక్టర్కి ఏమో 4 kilo ohms గ్రౌండెడ్ చేస్తాం. ఓకే, నెక్స్ట్ బేస్ టు నెక్స్ట్ కలెక్టర్ టు ద ట్రాన్సిస్టర్ 4 kilo ohms is given. Okay, now that base and the emitter of the previous transistor is connected to the base and the emitter is grounded, and once again the collector output is taken as RC2, that is nothing but 5 kilo ohms at plus V0. Given circuit has voltage shunt feedback, IF equal to minus V naught by RF, that implies IF by V naught equal to beta F, that equal to minus 1 by RF equal to minus 1 by 4 kilo ohms. Draw circuit without feedback. Draw circuit without feedback. Feedback తీసేస్తాం. Then the IS is parallel with RS is parallel with RF and given to base of the transistor, and the collector is given as RC1. The emitter is given to RE. The emitter output RE is given to the base of the next transistor, and then the emitter is grounded. The collector is given to parallel with RF, and RC2 is also parallel. The output is taken as V0. Output is taken as V0. Let Vt equal 25 millivolts, Gm1 equal to IC1 by Vt, that equal to 20 millimos, R pi 1 equal to beta 1 by Gm1, that equal to 150 by 20 equal to 7.5 kilo ohms. Gm2 equal to IC2 by Vt, that equal to 40 milliohms. Mos, R pi 2 equal to beta 2 by Gm2 equal to 150 by 40 equal to 3.75 kilo ohms. Replace Q1 Q2 with pi model. IS current source is parallel with RS dash. His input is given as R pi 1, and the emitter is given with RE. Then that beta BIB1, okay na, RC1. సో ఈ రెండు మెర్జ్ అయిపోయి బీటా B1 R pi 1 వచ్చింది కదా, దాన్ని మెర్జ్ అయిపోయి emitter దగ్గర 1 plus beta IB1 REకి ప్యారల్గా వస్తుంది కదా. దట్ IB2 will goes to R pi 2. R pi 2 is grounded, beta IB2 and RC dash V0. R I1 equal to R pi 1 plus 1 plus beta into RE parallel with R pi 2. R I1 equal to 204.46 kilo ohms. Use current divider. IB1 equal to IS into RS dash by RS dash plus R I1. V0 equal to minus beta IB2 into RC dash. V0 equal to minus beta into RC dash into numerator part 1 plus beta IB1 into RE whole by RE plus R pi 2. V0 equal to minus beta RC dash into 1 plus beta RE by RE plus R pi 2 into IS RS dash by RS dash plus R I1. V0 by IS equal to A, that equal to minus beta RC dash into 1 plus beta RE into RS dash whole by RE plus R pi 2 into RS dash plus R I1. A equal to minus 16.238. A is the transistance gain. Ri equal to Rs parallel with Ri1 190.3. R0 equal to Rc dash equal to 2.22 K. D sensitivity. D equal to 1 plus beta F. D plus minus 1 by 4 K into minus 16.238 K. D equal to 5.06. AF equal to A by 1 plus beta AF. That equal to minus 3.21 K. Minus 3.21 K. RIF equal to Ri by 1 plus beta F A equal to 190.3 by 5.06. That equal 37.6. ROF equal to R0 by 1 plus beta F A 222 by 5.06. That equal 439.13 ohms. Explain at least the 5 advantages and disadvantages of LVDT. State at least 2 uses of LVDTs. Advantages of LVDT: high range for measuring displacement ranging from 1.25 millimeters to 250 millimeters with 0.025% full scale linearity. It allows measurement down to 0.003 millimeters. Friction and electrical isolation: ordinarily there is no physical contact between the movable core and coil structure, which means LVDT is a frictionless device. It implies there is no wear out, and this gives LVDT larger life. Immunity from external effect: the separation between core and coils of LVDT permits isolation of media such as pressurized corrosive and caustic fluids from the coil assembly by adding a non-magnetic barriers interposed between the core and inside of the coil. It makes the hermetic sealing of coil assembly possible and eliminates the need of a dynamic sealing on moving member. The isolation also makes an LVDT an effective analog computing element without the need of a buffer amplifier. High sensitivity: it produces a highly sensitivity which is typically about 40 volt per millimeter. Ruggedness: these transducers can usually tolerate high degree of shock and vibration, especially when core is spring loaded without any adverse effect. LVDT are simple in construction and are stable and easy to align. Low hysteresis: LVDT shows a low hysteresis Enhance repeatability is excellent under all conditions. Disadvantages of LVDT: relatively large displacement is required for appreciable differential output, sensitive to stray magnetic fields, but shielding is possible. Transducer performance is affected by vibrations. The receiving instrument must be selected to operate on an AC signal, or a demodulated network must be used if a DC output is required. The dynamic response is limited mechanically by the mass of the core and electrically by the frequency of the applied voltage. Temperature affects the performance of the transducer. Temperature also causes phase shifting effects. Second question: the output of an LVDT is connected to a 5-volt voltmeter through an amplifier whose amplification factor is 200. An output of 2 mV appears across the terminals of LVDT when the core moves through a distance of 0.5 mm. Calculate the sensitivity of the LVDT and that of the whole setup. The millivoltmeter scale has 100 divisions. The scale can be read to 1/5 of a division. Calculate the resolutions of the instrument in millimeters. Sensitivity LVDT equal to output voltage by displacement, that equal to 2 into 10 power minus 3 by 0.4, that equal to 4 into 10 power minus 3 volt per millimeter. Sensitivity of instrument equal to amplification factor into sensitivity of LVDT, that equal to 200 into 4 into 10 power minus 3, that equal to 0.8 volt per millimeter, that equal to 800 millivolts per millimeter. One scale division equal to 5 by 100 equal 50 millivolt. Minimum voltage that can read on the voltmeter equal to 1/5 into 50, that equal to 10 millivolts. Resolution of instrument equal to 10 into 1/800, that equal 0.0125. In the series RL circuit, the switch is in position while long enough to establish the steady state is switched to position 2 at t equals 0. Find the current I. Okay, now for this at t equals 0 minus the inductor reaches steady state, that is it acts as short circuit for DC supply. So 50 volts is in circuit of 20 ohms. So IL of 0 minus equal 50 by 20 equal 2.5 amperes. IL of 0 plus equal 2.5 amperes for t greater than 0. Apply Laplace transform to the circuit, then what will happen? 20 ohms is in series with minus plus L I naught equal to 2.5 into 0.5, that equal 1 volts. 20 ohms is in series with minus plus 1 ohms, 1 volts in parallel in series with 0.4 S. So I of S equal to 1 by 0.4 S plus 20, that equal 2.5 by S plus 50. Apply inverse Laplace transform, then you will get I of t equal 2.5 into e power minus 50t for t greater than equal to 0. Obtain the overall ABCD parameters of the circuit. Z series lo parallel Y, దానికి parallel గా 1 వైండింగ్, n:1 1కి ఇంకో వైండింగ్. ఓకేనా, ట్రాన్స్ఫార్మర్లా వస్తుంది. ఓకేనా, నౌ ఫర్ దిస్ టు క్యాలిక్యులేట్ పారామీటర్స్ we write it as Z. First we will take it as the primary windings. Zకి పక్కన Y ప్యారల్ తీసుకొని Zకి ఇన్పుట్ V1 కరెంట్ I1, Yకి అవుట్పుట్ V2 కరెంట్ I2. V1 ఈక్వల్ టు ZI1 ప్లస్ V2, I1 ఈక్వల్ టు YV2 మైనస్ I2. Applying KVLs, substituting equation 2 and equation 1, V1 equal Z of minus I2 plus YV2 plus V2, V1 equal to 1 plus YZ V2 minus ZI2. Compare equation 2 and 3 with ABCD parameters. V1 equal to AV2 minus BI2, I1 equal to CV2 minus DI2. ABCD means 1 plus YZ ZY1. Then V1 means I1. So input transformer ki n:1 వస్తుంది కదా. Input current I1, input current I2, V1 V2 windings. V2 by V1 equal to 1 by n, I1 by I2 equal to minus 1 by n, V1 equal to n V2, I1 equal to minus 1 by n, I2, ABCD equal to n0 0 1 by n. Two cascade networks ABCD 1 plus YZ ZY1 convolved with n0 0 1 by n. ABCD means n into y plus 1 plus y z by n, ny 1 by n. That is about the ABCD parameters. Determine the functional behavior of the circuit. Assume the input W is driven by the square wave signal. Here JK flip flop, 2 JK flip flops are there. A clear is there. Clear is given as a bubbled ఒకదానికి ఉంది, without bubble ఒకదానికి ఉంది. Clock is given as both has given clock. The second flip flop output is given to first J, that is feedback, Q to J, Q to J straight, Q1 Q. Okay, this is the circuit. In the given circuit, consider the left flip-flop as FF2 and right flip-flop as FF1. Given circuit redone as given below. Then Q1 JK2, then first flip-flop gives you J2 Q2 K2 Q2. Second flip-flop J1 Q1 K1 Q1 bar. Flip-flop 2 and flip-flop 1 are having positive edge trigger clock. W is basically clock input of the circuit. KT input of flip-flop 2 may be 0 or 1. Clear input is asynchronous input for both FF2 and FF1, and it may be 0 or 1. FF2 is having active low asynchronous clear input. Its clear input of FF2 is 0. Irrespective of W input, FF2 output is 0. If clear input of FF2 is 1, after applying W input, FF2 will follow the truth table of JK flip-flop. FF1 is having active high asynchronous high clear terminal. If clear input of flip-flop 1 is 1, irrespective of W input, flip-flop output is 0. If clear input of a flip-flop is 0, after applying W input, FF1 will follow the truth table of JK flip-flop. Case 1, clear 0. FF2 output is 0, so FF1 J1 equal to 0 and K1 equal to 1. After applying W input, flip-flop output is 0. Case 2, clear equal to 1. Flip-flop 1 output is 0, so flip-flop 2 J2 equal to 1. If K2 equal to 0, then flip-flop 2 output is 1. If K2 equal to 1, then flip-flop 2 output is complement previous state after applying W input. In the circuit shown in the figure below, the gate voltage Vg is very small. Assume op amp is an ideal op amp. Vtn equal to 1 volt and mu n COX omega L equal to 200 microamperes per V square. Calculate output voltage. The circuit diagram is this is N channel MOSFET. Okay na, this source has minus 2 volts. Drain is connected to negative terminal of the op amp. Positive terminal is given 4 volts. Then feedback of the op amp is 20 kilo ohms. V out. So you know that mu n COX into W by L equal to 0.2 milliamp per volt square. Vt equal to 1 volt. Okay na, given Vg is very small. Vgs equal to Vg minus Vs equal to 0 minus of minus 2 equal to 2 volts. Vds equal to Vd minus S equal to 4 minus of minus 2 equal to 6 volts. Vds greater than Vgs minus Vt. MOSFET is in saturation. Then the equation is IDS equal to mu n COX by 2 into W by L into Vgs minus Vt whole square. IDS equal to 0.2 by 2 into 2 minus 1 whole square milliamperes. IDS equal to 0.1 milliamperes. KCL V0 minus 4 by 20K equal to IDS. V0 minus 4 by 20 equal to 0.1. V0 equal to 6 volts. Describe the construction working of a shunt type ohmmeter. Write down its design equations. The circuit diagram of shunt type ohmmeter is shown in figure. Okay na, the how it is means E is series with R1. దానికి E in series with switch. R1 ki switch ki parallel ga 1 Rm. The current is nothing but Im. The inward current is I1. Outward current from the node is Ix. That output parallel resistance is Rx. AB is connected taken as Rx. The circuit diagram of shunt type ohmmeter shown figure consists of a battery in series with an adjustable resistor R1 and basic D R and a basic D orthogonal movement meter. The unknown resistance is connected across terminals A and B parallel with the meter. In this circuit, it is necessary to have an off-on switch to disconnect the battery from the circuit when the instrument is not in use. When the unknown resistor Rx equals 0 ohms, A and B are shorted. The meter current, if the unknown resistance Rx equal infinite and B are open, the current finds path only through the meter, and selecting a proper value of resistance R1, the pointer may be used to read full scale. This ohmmeter therefore has 0 mark on the left hand side of the scale, no current, infinite mark on the right hand side of the scale, full scale deflection current. The analysis of the shunt type ohmmeter is similar to that of a series type ohmmeter. In the figure, when Rx equal to infinity, the full scale meter current is IRS equal to E by R1 plus Rm. R1 equal to E by IFS minus Rm. E by IFS is separate, minus Rm is separate. With any resistance Rx to be measured, the meter current Im is Im equal to E whole by R1 plus R1 separate denominator part చెప్తున్నా R1 plus Rm Rx by Rm plus Rx Rm Rx by Rm plus Rx అది separate E by R1 plus Rm Rx by Rm plus Rx ఇది into Rx by Rm plus Rx that equal to E Rx by R1 Rm plus Rx into R1 plus Rm at half scale reading of the meter Im equal to 0.5 IFS and Rx equal to RH then 0.5 IFS equal to ERH by R1 Rm plus RH into R1 plus Rm dividing equation 1 by equation 2 gives S equal to Im by IFS that equal to Rx into R1 plus Rm whole by R1 Rm plus Rx into R1 plus Rm. Usually R1 is very large as compared with Rm and therefore S equal to Im by IFS that equal to Rx by Rm plus Rx. Thus the meter can be calculated by computing the fraction of full scale S for a given resistance Rx in terms of Rx and then meter resistance Rm. Meter resistance Rm. In order to determine the relative scale values a given value of R1, the half scale reading may be found by dividing 1 by 2 and solving for RH. RH equal to R1 Rm by R1 plus Rm. It is clear from the above analysis that the battery EMF E, the meter field scale current IFS and meter resistance Rm determine the resistance R1. The resistance R1 and the meter resistance Rm determine half scale resistance RH. Thus the meter resistance scale depends only on the meter, the voltage of the battery. The voltage of the battery. The battery EMF is 1.5 to 15 volts with the full scale current of the meter may vary from 0.25 milliamperes to 1 amperes or even more. Thus then R1 will vary from 5 to 12,000 to 1 to 302. Usually R1 is considerably larger than Rm. Then R1 plus Rm equal to R1. Substituting this in equation 3 gives RH equal to Rm. The shunt type ohm meter is particularly suited for the measurement of low value resistors. It is not commonly used in instrument but it is used in laboratories for low resistance applications. The ohm meter shown in the figure uses a 100 ohms basic movement requiring a full scale current of 1 milliamps. The internal battery voltage is 3 volts. The desired scale marking for half scale reflection is 2000 ohms. Calculate the value of R1 and R2 and the maximum value of R2 to compensate for a 10% drop in the battery voltage. సర్క్యూట్ ఏమంటే ఆర్ఎం అని ఉంటుంది ఫస్ట్, దానికి ప్యారలల్గా రియోస్టాట్ R2 అని ఉంటుంది, వేరియబుల్ రెసిస్టెన్స్ R2 ఓకేనా. దానిపైన సిరీస్ విత్ R1 అది పాయింట్ ఏ, కింద ఈ పాయింట్ బి, ఏబి మధ్యలో RX ఓకేనా. ఏబి మధ్యలో given IFSD equal to 1 milliamps, Rm equal to 100 ohms, RH equal to 2000 ohms, E equal to 3 volts, R2 equal to IFSD Rm RH whole by denominator part to E minus IFSD RH, R2 equal to 200 ohms, R1 equal to RH minus numerator part IFSD Rm RH whole by E, R1 equal to 193.33 for 10% voltage drop. E equal to 3 minus 3 into 10 by 100, 3 minus 0.3 that equal to 2.7 volts. R2 equal to numerator part IFSD Rm RH whole by denominator part E minus IFSD RH, R2 equal to 285.71. R2 should be changed from 200 ohms to 285.7 ohms to compensate for this reduction in battery voltage. A series resonant network consists of a 50 ohms resistor, a 4 millihenries inductor and a 0.1 microfarad capacitor. Calculate values of omega naught, f naught, q naught, bandwidth omega 1, omega 2, Z in at 45 kiloradians per second, and the ratio of magnitude of the capacitor impedances to resistor impedances at 48 kiloradians per second. Series RLC, R equal 50, L equal 40, C equal 0.1 microfarads, omega naught equal to 1 by root LC, f naught equal to 1 by 2 by root LC, q equal to 1 by r into root L by C, bandwidth equal to omega 2 minus omega 1 equal to r by L, omega 1 equal to minus r by 2L plus root over r by 2L whole square plus 1 by LC, omega 2 equal to 1 r by 2L plus root over r by 2L plus 1 by LC, Zn equal to root over x r square plus xl minus xc whole square, xl equal to omega L, xc equal to 1 by omega c, xc equal to 1 by c, 1 by omega c, xc by r equal to 222.22 by 50 that equal 4.44.